Consider a standard solar-powered pocket calculator from 1980. It can solve complex arithmetic like finding the square root of 739,482 in milliseconds, a task that would take a human minutes of focused concentration. Yet that same calculator cannot recognize a coffee mug, walk across a room, or learn to play tic-tac-toe. Today's most advanced artificial intelligence systems are incredibly powerful, but they are still fundamentally like that calculator, highly specialized. We call this narrow AI. It excels at specific tasks, like predicting protein structures with AlphaFold 2 or matching chess moves with Stockfish to 15, but completely collapses if you ask it to do anything outside its pre-programmed domain. To understand artificial general intelligence, or AGI, we have to look at how humans learn. A 3-year-old child can play with a toy kitchen, watch their parent cook, and instantly transfer those basic spatial concepts to opening a real refrigerator. In computer science, this is known as transfer learning. Narrow AI struggles immensely with this. A neural network trained on millions of games of StarCraft cannot play a single round of Super Mario without being completely retrained from scratch. AGI represents a hypothetical system that possesses the fluid capability to transfer knowledge across completely unrelated domains. It is not just about speed or memory. It is about the adaptive capability to learn, reason, and solve novel problems without human intervention. Because intelligence is notoriously difficult to define, computer scientists rely on specific benchmarks to test the boundaries of AGI. Legendary computer pioneer Alan Turing proposed the famous Turing test in 1950, focusing entirely on natural language deception. However, modern researchers like Steve Wozniak suggest more physical milestones, such as the coffee test. In this scenario, a robot must enter an average, unfamiliar American home, locate the kitchen, find the coffee maker, identify the ingredients, and brew a cup entirely on its own. Another rigorous benchmark is François Chollet's Abstraction and Reasoning Corpus, or ARK, which tests a system's ability to solve brand-new visual puzzles it has never encountered before, measuring raw learning efficiency rather than memorized data. The primary catalyst driving us toward AGI today is the transformer architecture, introduced by Google researchers in the seminal 2017 paper, "Attention is All You Need." Traditional neural networks processed information step by step, but transformers use a mathematical mechanism called self-attention to process entire datasets simultaneously. By calculating high-dimensional vector representations of words and concepts, these networks map semantic relationships across billions of parameters. When scaled up with massive compute power, measured in millions of petaflops, these models exhibit emergent abilities. Sudden, unplanned capabilities like basic logic and code generation that were never explicitly programmed into the training run. Despite the illusion of deep understanding, modern large language models operate primarily on next token prediction, calculating the probability of the next word based on historical patterns. This leads to a critical bottleneck: hallucination. Because the model lacks an underlying physical world model, it cannot verify the truth of its outputs. It does not actually know that water is wet or that dropped objects fall. It only knows that the word drop is statistically likely to be followed by ground. To bridge the gap to true AGI, systems must transition from passive pattern recognition to active reasoning. They need to construct mental simulations of cause and effect, allowing them to plan multiple steps ahead before generating an action. Building the physical infrastructure for AGI requires astronomical resources. Training a frontier model like GPT-4 required an estimated 25,000 NVIDIA A100 GPUs running continuously for several months, consuming roughly 50 gigawatt-hours of electricity. To scale this to true human-level AGI, tech companies are planning data centers requiring up to 5 gigawatts of power, equivalent to the output of 5 nuclear reactors. This massive energetic demand creates a stark physical constraint. While a human brain operates on approximately 20 watts of power, barely enough to light a dim bulb, our current path to artificial intelligence demands millions of watts to achieve similar cognitive flexibility. When true AGI is finally realized, it will mark a profound inflection point in human history. Unlike human experts who specialize in a single field, An AGI system could simultaneously master quantum physics, structural engineering, and macroeconomics. This could lead to recursive self-improvement, where the AGI designs an even smarter version of itself, triggering an exponential intelligence explosion. The transition from tools that merely assist us to autonomous entities that can independently discover new scientific laws forces us to confront fundamental questions of alignment and control. Ultimately, the quest for AGI is not just a technological race. It is a mirror reflecting our deepest questions about the nature of consciousness, agency, and what it truly means to think.